All right, so I will give you the punchline of this chapter. This entire chapter is essentially based on the fundamental theorem of calculus. Okay, and you guys have learned the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus, well, integration and derivatives are inverses of each other. Okay, so if you have the integral of a perfect derivative, the fundamental theorem of calculus says this is equal to fx evaluated at the endpoints equal to fb. Okay, so what the fundamental theorem of calculus did was, when you integrated this, you took the derivative and you integrated that, you got back your function. Okay? And the value of this integral, of this definite integral, was just this function evaluated at the endpoints. All right, so we'll keep that in mind, and essentially the entire chapter is based on that. Yeah. All right, so one of the things we learned was how to calculate the work done by a force. Okay. So let's say you had a force acting on an object, and if this force was constant when the object moved in a straight line, and d was the displacement vector, the work done was given by the dot product of the force vector and the displacement vector. Okay, so it was f d cosine theta. Okay, and then so we learned this last time, and then we generalized this to the case the object is still moving in a straight line, but we let the force change. When the force varied, here's how you calculated the work done. So here was the displacement, and as the object moved, the force was varying. Okay. So how did we calculate the work done in that case? Well, so if you go back to this expression and look at this expression, the way the work was calculated is f cosine theta is the component of the force along the displacement. So you can think of that as the x component if that's the x direction. Okay, so it was the x component of the force times the x displacement in the x direction. All right, so when the force changed, what did you do? You broke up this displacement into small pieces. And what you said was, how small a piece did you break it up into? Oh, okay, you break it up into small enough piece where the force remains constant over that piece. Okay, and now you know how to calculate the work done on that small piece. So x component of the force, I'm writing it as a function of x. That's the x component of the force at location x times dx. Okay. So that's the work done over this piece. You can put subscript I telling you it's over the piece I, and then you sum up all those little pieces. Okay. That's the work done over this piece and so on. Okay. Okay, so that was the work done. All right, so that was, your object is still moving in a straight line, and you let the force change over that distance. Okay. Then the third case was, now you generalize everything. Okay, you generalize the trajectory and you let the force change as well. Okay, so your object is moving from this point to that point. And then what you did was, well, okay, you know calculus, all you have to do is break up your trajectory into little pieces, calculate the work done over that little piece. Okay, you already know that work done over a small displacement is this dot product, and then sum over all little displacement, which is just the integral. Okay, so that was the line integral. Okay. So that's for a general trajectory for any varying forces. Yep. Now let's get back to this case, the second case. We'll keep it simple. This is an object moving in one dimension, but the force is changing. Okay? So now we ask the following question. What if this force is du by dx? Okay. We're always interested in calculating the work done by a force. What if this force is given by that, by the derivative of a function? Okay. How much work is done in going from x initial to x final? Okay. How much work is done on this object when it goes from x initial to x final? All right. Does this look familiar? Okay, here you're taking the integral of a derivative, and so you can use the fundamental theorem of calculus. It would be u x final minus x initial. Okay. So this would be u x final minus. All right. Now, for later convenience sake, we define this with a negative sign. All right. So we'll spend 30 seconds on this slide because this entire chapter is based on this slide. Okay. So if you understand this, then that's the punchline on the chapter. Okay. So the point is the following. Okay, you have a force acting on an object. Okay, it's a function of position. You want to be able to calculate the work done by this force on this object as it moves from the initial point to the final point. Okay, what we are saying is if this force can be expressed as the derivative of a scalar valued function. What do you mean by a scalar valued function? A function that spits out a scalar. Okay. If this force is given by the derivative of this function, then the work done is very easy to calculate. It's just the value of the function at the end point minus the value of the function at the initial point. Okay. So work done by that force is very easy to calculate. Okay. And we like it if life gets easier for us. Okay. All right, so if you have such a force, we even give it a special name. This force is called a conservative force. Okay. And if you cannot express a force like that, then it's a non-conservative force. All right. So in this entire course, in Physics 1 and 2, you'll see only 3 conservative forces. The force of gravity, the spring force, and the electrostatic force, which you'll see in Physics 2. Okay. And what's special about these forces? These forces can be written as a derivative of a scalar valued function. Okay. And what was the big deal about that? Well, the work done by those forces is just the negative of this function evaluated at the final point minus the function evaluated at the initial point. Okay. So work done by these forces is very easy to calculate. Okay. And work done is negative of this function. this function, okay, we'll generalize it. This is for one-dimensional case. We'll generalize it to three-dimensional case. Okay, this is called the potential energy function. Okay. So for gravity, right now we'll consider the simplest case. The potential energy just depends on the vertical coordinate. Okay, so the potential energy depends on the y coordinate is mgy. Okay. In chapter 13, when you start dealing with larger planetary size objects and stuff like that, you will learn that this potential energy function depends on the distance, the center of mass distance between the two objects. Okay. So right now, if you're on Earth and you're not going too far from Earth and acceleration due to gravity is constant, then this is the potential energy function. Okay. That function is an approximation of this function, but this guy is a pain in the neck to use. Okay. So right now we'll use this. Okay. For the spring force, the potential energy function is given by 1/2 kx squared. And that's the entire chapter. All right, so I'm going to pause 2 seconds and then say what I said briefly again and before we get into the slides. And I'll let you guys ask questions if you have any. So what we are interested in is calculating the work done by forces. Okay. Right now, we'll let the object move in one dimension. Okay, so that'll be our x-axis. The location will be given by its x coordinate. And this is the x component of the force as a function of position. Okay. So the work done by this varying force is equal to this integral. And, well, we learned the fundamental theorem of calculus in our calculus classes. So what we said was, well, what if this force could be written like so? Okay. Then this integral is very easy to do. Okay. So substitute that force, and the integration undoes this. So the integral is that. And the work done was equal to that. Okay, the work done was the change in the potential energy function, negative of the change in potential energy function. Okay. The change in anything is the value of that thing at the final point minus the value of that thing at the initial point. The change in your bank balance is your bank balance at the final point minus the bank balance at the initial point, right? All right, so calculating the work done by such forces is very easy. And these guys are called conservative forces. And if a force cannot be written like this, it's a non-conservative force. So these guys are conservative forces. And let me give you examples of non-conservative forces. When you push on an object, that's a non-conservative force. Friction is a non-conservative force. The force a rocket exerts on an object, okay, is a non-conservative force. your car engine exerting a okay. These are all pushes, examples of pushes. Okay. So, in a lot of examples, most of the forces that you encounter are non-conservative forces. Okay? And then if you want to calculate the work for these non-conservative forces, you actually end up having to do this line integral. Okay, so in most cases, calculating the work done is not easy. Okay, so if you want to calculate the work done by the Falcon 9 in going from point A to B, getting from launch pad to the orbit, that's not easy to calculate. Okay, you'd have to do this line integral. All right. Okay, so we understand this. The chapter is about forces that are given as derivative of a scalar valued function, and this is called the potential energy function. Okay. All right, so let's get into the slides. So we understand what potential energy is associated with. Potential energy is associated with forces that are called conservative forces. Okay. We'll come to this part in the latter half of the chapter, energy conservation. So, what are conservative forces? So here are them in one dimension. Okay. So this is a conservative force. Okay. All right. Work done by a conservative force on a particle moving between 2 points is independent of the path. All right, so let's try and understand this statement. Okay, so let's go back to our thing. Work done by that force in going from x initial to x final was equal to that function evaluated at the final point minus that function evaluated at the initial point. Okay, so when this object went from here to there, that's how much work was done. When this object went from here to there and then back, how much work was done? Same amount. From here to there to here to there to here to there. Same amount. Okay? So that's what we were saying there. Okay? It's independent of the path. Yeah. Friction is a non-conservative force. Work done is path dependent. Okay. When the book goes from here to there, the work done by friction is different when the book goes from here to there along that path. Okay. If you were pushing this book, that is a non-conservative force. The work you do in pushing the book from here to here is different than the work you did in pushing the book from here to there. Okay, along that path. So what is the potential energy function? And I'm sort of jumping all over the place, but So this is a conservative force. And this is the potential energy. That is the potential energy function. All right. So when you kick a football, we'll ignore air resistance. Drag forces are non-conservative forces, so we'll say drag forces are negligible compared to any of the other force acting. So in this case, if you can neglect drag forces, gravity is the only force acting on this object. And as the ball rises, what is happening is its potential energy is increasing and its kinetic energy is decreasing. Okay? And the sum of the two remains constant. Okay? At all points of the trajectory, the sum of the potential and kinetic energy will be constant. And that is the conservation of mechanical energy. That was that statement, energy conservation. Okay? Well, that was specifically mechanical energy conservation. Okay? So, so when you kick a football, its potential energy increases and its kinetic energy decreases, and the sum of the two energies will remain constant. So here's another example. Okay, so if there's no friction on this roller coaster, as the roller coaster rises, its potential energy is increasing. Okay, its kinetic energy is decreasing. So as it's rising, it's slowing down. Okay, and then as it falls over that, its potential energy decreases and its kinetic energy increases. It's going faster. But the sum of these two, the total mechanical energy remains constant. All right, so that is the potential energy function. Okay. So when can you define a potential energy? You can define potential energy for conservative forces. Okay? I mean, that was the definition. Conservative force is negative of du by dx. Okay? So the work done by a conservative force is negative of change in potential energy. Okay? We're just stating this guy. Work done by a conservative force is negative of change in potential energy. Okay? So that's the statement. Okay, so this is work done by conservative forces, change in negative of change in potential energy, or change in potential energy is negative with the work done. In 1 dimensions, that's the case. In 3 dimension, the work done by that force would be this line integral. Okay. And we'll come to, so we'll do everything for the 1-dimensional case, and then we'll generalize to 3 dimensions. Okay. Okay, now what we're going to do is the following. I told you that the gravitational potential energy is mgy. I'm going to derive that now. Okay. So when g is constant, the gravitational potential energy is mgy, and we're going to show that to you now. All right, so let's say an object moves from here to there. Gravity is the only force acting on it. That means, and what we're saying is drag and all other forces are negligible. Okay, so the work done by gravity is the gravitational force. So our y-axis is pointing up. Okay. And the gravitational force is pointing down. So mg, that's the magnitude of the force. It's pointing in the negative direction, so negative mgj. So there's the force. And so the work done is this generalization, force dr. Okay, and our object is moving along the y-axis. So there's the force, there's the vector notation for the force, dotted with dyj. We're dropping the object. Okay, j dot j is 1. Okay, and so that is equal to minus mg dy. Yeah. Y initial to y final. That's equal to minus, and integral of 1 is y, so it's mg is a constant. Remember, we're close to the Earth, and g is constant. Okay. For instance, if you jump, let's say if you jump 100 kilometers, then g would be a function of y. But you're not going to jump 100 kilometers, okay? Not for now. Okay. So we are going to say g is constant, y. Okay. And so this is minus mgy final minus mgy initial. Okay. And there's the potential energy function. Okay. So what we have done here is just derive that, show you that the gravitational potential energy is given by mgy as long as g is constant. Okay. All right. Now we'll do the same thing for a spring. Okay. The spring force is given by minus kx. The force that the spring exerts on an object is minus kx. This is called Hooke's law. The work done by the spring force is my integral of minus kx dx. And that integral is, of course, minus k is constant. Integral of x is x squared by 2. X initial to x final. So minus 1/2 k x final squared minus k x initial squared. Okay, so there's your potential energy function. Okay, those are the only two conservative forces we'll deal with. The electrostatic force we'll talk about in physics too. Yeah. What is the big deal about conservative forces? What's so great about them?
Easy to work with.
Huh?
Easy to work with.
It's very easy to calculate the work done by these fellas. Okay? You just have to evaluate the function at two different points, at the final point and the initial point. Okay? It doesn't care what the path was, okay, in getting from the initial to final point. Okay? So what does that mean in real life, for instance? So here's what that would mean. So if this ball had no friction, the only forces, there was no friction on the ball, the only forces acting on the ball would be the force of gravity and the normal force. The normal force doesn't do any work. Okay? All it does is change the direction of motion. Okay? So what that would mean is if there was no friction, this ball at the end would have the same speed, irrespective of the shape of this slide. That's what that means. The work done is independent of the path. It depends only on the initial and final location. So the ball would come out at the same speed, whether that was the track or this was the track. And so this is relevant in roller coasters. Okay? So different designs have different excitement factors. Okay? All right. Okay, so the spring potential energy is given by 1/2 kx squared. All right, so now let's see what this statement means. Conservation of mechanical energy. What does this mean? That mechanical energy is constant throughout the motion of the object, throughout the evolution of the object. Okay, so you saw the work energy theorem. The net work done, that is the work done by all the forces acting on an object, is equal to change in kinetic energy. So this is a theorem we saw in the previous chapter. Okay. Now let's say if only conservative forces are acting on the object. What does that mean? There's no friction acting on the object and nobody's pushing on stuff. Okay. And there's only conservative forces acting on the object. So what are we saying? What are the conservative forces that you know about? And? Yep. So these are the only two allowed forces acting on it. So let's say for now only gravity is acting on it. Do you know how to calculate the work done by gravity? Yes, you do. It's minus U final, that is the potential energy at the final configuration, minus U initial. All right. And that's minus. We'll bring this to that side. Minus of minus is plus, and we'll bring this guy to this side. So KE initial plus U initial equal to KE final plus U final. Look at this. This is pretty good. This quantity, the kinetic energy plus potential energy at the initial point is equal to the sum of kinetic energy plus potential energy at the final point. All right. So what is the case we're considering? Let's say only the force of gravity is what we're considering. Okay, so you drop a ball. What this equation is saying is the sum of kinetic and potential energy is equal to sum of kinetic and potential energy at the final point. Which one is the initial point? Which one is the? Huh?
Where it's dropped from?
Which one is the final point?
Ground.
Okay, anything can be the initial point, anything can be the final point. That means the sum of these two quantities is constant throughout the process. Here's this chalk. I'll throw it up. The energy is constant at every point. Okay, so you can make powerful statements like that. Okay. Going back to this. All right, so you can have a complicated ride like that as long as there is no friction. Okay, the speed varies dramatically depending on the shape of the slide. But no matter how complicated this is, now you've learned a very beautiful fact to state about this. The sum of potential plus kinetic energy at every point is constant. Yeah? And that's a beautiful thing. So we like to be able to say stuff like that. Okay? We like to find constants of motion. Okay? And you can say that as long as you have conservative forces acting on your system. Okay? If you attach Elon Musk's rocket, then all bets are off. But so that's the statement. Conservation of mechanical energy. Kinetic plus potential energy is called mechanical energy. And so the mechanical energy is constant for this motion. Okay? So you can have a bouncy ball, and if it bounces back to its original height, okay, its mechanical energy will remain constant. Okay? And how long would that ball bounce? Indefinitely. Okay, so if it bounces back to the same height the first time, it'll bounce back to the same height the second time. Okay, so here's the sum of potential plus kinetic energy is constant. Okay, when you see that, what does that mean? There's no friction in the system. Okay? So non-conservative forces are absent. So what is a non-conservative force? A force that cannot be written as du by dx. Okay, that's a non-conservative force. The work done by such a force is path dependent. your push friction forces are non-conservative. Okay. All right. So you saw that here was this is the work energy theorem. That is the net work done by all forces, conservative, non-conservative, doesn't matter. Okay. The sum of work done by all forces is equal to change in kinetic energy. Well, let's say, so there are only two kinds of forces, conservative and non-conservative forces. The work done by conservative forces is easy. It's change in potential energy. Okay. So, work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. Okay. So, and this is equal to change in mechanical energy. Okay, so change in kinetic energy is KE final minus KE initial. Similarly, U final minus U initial. And so that is equal to KE final plus U final minus KE initial plus U initial. And this is mechanical energy. So that's change in mechanical energy. So non-conservative forces change the amount of mechanical energy in the system. Okay? So when your car engine acts, it changes the kinetic energy of your object, of your car. If you're driving on a flat road, your potential energy is not changing. Okay? Friction forces. Okay. So friction forces. The work done by friction force is easy to calculate. The work done by friction force is magnitude of friction force times cosine 180. Okay. Which is, okay. So the work done by friction force is also easy to calculate. Okay. So you saw that the work done by non-conservative force is equal to change in mechanical energy. I'll write it like so. But we'll split U pushing on the cart versus this. The part by friction force is easy to calculate, is change in mechanical energy. Yeah. And we'll bring the friction force, the work done by friction force on this side. What does friction do? I'm sorry?
It creates heat.
It reduces mechanical energy. It converts mechanical energy to heat, thermal energy. Okay? So the change in mechanical energy plus the change in thermal energy is equal to the work done by all the other non-conservative forces. This energy is the thermal energy. Increase in thermal energy is that much. Okay? Mechanical energy decreased by that much, and thermal energy increased by that much, and that's what that is. So here's the overall statement on conservation of energy. If you account for all kinds of energies, change in mechanics for an isolated system. So for an isolated system, if you account for all kinds of energies, change in mechanical energy plus change in thermal energy plus change in internal energy equal to 0. What this means is, if you take into account all kinds of energy, one, I'm going to say two, Okay, so if you account for all forms of energy, okay, the total energy of a system does not change. And this is true for all sized finite, for all isolated systems as far as we know. Yeah. What is the biggest isolated system? So assuming the universe is finite, that's the biggest isolated system. Okay. So as far as we know, okay, if the universe is finite, then its total energy must be conserved. All right. So here's a object attached to a spring, or we can see it. Okay, so you can think of this. Here's a mass attached to the spring. Okay. When you push this, so this is the equilibrium position of the of the glider. If you push it to the right, this spring compresses, this spring stretches. Okay. When a spring compresses or stretches, its potential energy increases. That's its potential energy. When x is positive or negative, the square is positive, its potential energy increases. So when its potential energy increases, when you push it to the right, its potential energy increases. When you push it to the left, its potential energy increases. Okay. When this thing is moved to the right, which way are the forces, which way is the force on this object? If you push this guy, if you take this guy to the right and let it go, which way will it move? Back to left. If you push it to the left, it'll move to the right, the forces. Okay, what is the spring trying to do? It's trying to decrease its potential energy. Okay? And you see that's what's in this equation. The spring force is minus du by dx. Okay, if this derivative is positive, the force is in the negative direction. Okay. If this derivative is negative, the force is in the positive direction. Okay. So the forces that come into play are trying to decrease the potential energy of the system. Okay. That's the direction in which the forces act. All right, so if you want to describe a system, you want to be able to tell what is the force that acts on a system in any configuration. Okay, so if you know the force acting on a system in any configuration, then you can describe the dynamics of the system. You can describe how the system will evolve. Okay, and now you just learned that, well, you can give this function or you could give this function, because once you have this function, then you can calculate that function. Okay, so the potential energy curve is a very useful curve. You give the potential energy curve for a system. You from this you can determine the behavior of that system. Okay, so this is a description. This tells you how to. This is a good description of the system. Okay. So potential energy curves. Okay, so here's this mass. When the mass is at this location, there's the potential energy. And what are the forces that wanting to do? The forces are forcing the system back to equilibrium. Okay, so that's why that's called a restoring force. If you compress the system, if you put it there, there's the potential energy, and the forces are in this direction. Okay, they're bringing back the system to the minima of the potential energy. Okay, so the minima of potential energy. The minima of potential energy is a stable equilibrium point. Okay, So the forces are such that, see, when du by dx is positive, the force is in the negative direction. When this is negative, negative of negative, the force is in the positive direction. Okay. Okay, so this, okay, this is a stable equilibrium point, a stable equilibrium point. This is an unstable equilibrium point. Okay. Why is this unstable? Du by dx is negative. Negative of negative is positive. At this location, the point will run away from that equilibrium position. Okay. Here du by dx is positive. Negative of that would be, the force will be in that direction. Okay. So this is an unstable equilibrium position. This is a stable equilibrium position. So local minima of the potential energy function are stable equilibrium points. And these are unstable equilibrium. All right, so for the one-dimensional case, the force is given by minus dux by dx. In 3 dimensions, force is given by the gradient, negative of the gradient of the potential energy function. Okay. This operator so in 3 dimensions, here is the potential energy function. Again, this is a scalar valued function. What does that mean? Scalar valued. At every location, this function is spitting out a number, a scalar. That's what a scalar value does. Okay. This guy is a vector valued function. At every location, it's spitting out a vector. Okay. Do you guys know what this gradient operator is? What does this do? Have any of you guys seen it in any of your calculus classes yet? All right, so this is what it does. Anybody? Yeah, you've seen it?
I've never seen it, but I could assume what it does.
Okay, what does it do?
Well, if one gives the magnitude, the other gives how far. So you can have
This one and this one, they're not. You know. All right, so now is a good time to learn about it. Okay, so let's say you have a function like this, x, y, z. Okay, and heck, we can even do an example. I'm doing a very simple example. Okay. So at every location, you can evaluate the function. Okay. So let's say, and now I'm not going to put down numbers for this function. I'm just going to put down this number. Let's say u at this location is 100. At this location is 102, 104, 107, 98, 97, and so on. Okay, so here's the x-axis, y-axis, z-axis. At every location, you've evaluated the value of the function. Okay. Now you want to ask the question, in which direction is u increasing the fastest? Is that a valid question? I'm sorry? I'm sorry?
In the z direction.
How do you know?
Going based off the points. They might be going the right direction.
Yeah, so that, what you do understand, you understand the question. In what direction is u increasing the fastest? Okay? And at what rate is it increasing? And that's what the gradient operator does. Okay? So the gradient of u gives you the direction and magnitude of the fastest increase. Yep. And how's the gradient operator defined? Del u by del x I. You guys understand del u by del x, partial derivative of u? How many of you have seen partial derivatives? Okay. How many of you have not seen partial derivative? Okay, so you'll see that in 1 second. Okay. So you talk about partial derivatives of multivariate functions, functions that are dependent on multiple variables. Okay, what does del u by del x mean? Del u by del x means, let's say if you want to evaluate del u by del x at a given location, how is u changing if you're moving along the x-axis? For unit distance moved along the x-axis, parallel to the x-axis, how much did u change?
It's constant.
I'm sorry?
Is it constant?
Well, no, I will show you it's not constant. What does del u by del y say? How much did u change if you went parallel to the y-axis? What does del u by del z say? I forget. Tell me.
How much you change the z-axis?
Yeah, how much u changes if you move parallel to the z-axis? That's what those partial derivatives tell you. Okay. All right. So let's evaluate the derivative, the gradient. Okay, so for our function, u equal to x squared y cubed plus z to the power 4, the gradient of u, I've written a vector because the gradient is a vector field, okay, is equal to del u by del xi. Okay, the change in u when you move parallel to the x-axis, del u by del y j plus del u by del z k. Okay, here's how you get the partial derivative. Okay, when you're taking derivative with respect to x, you treat all other variables as constants. Okay, so what is del u by del x? Well, these are constants. Derivative of x squared is 2x, so it's 2x. Okay. What is del u by del y?
X squared x squared 3y to the second power and z.
Because he was taking the derivative of each
No.
axis.
You're taking the partial.
Yeah. Yeah, whatever you're taking the derivative with, that's the only thing that is changing. Remember we said, oops, I erased this. We were interested in u changing when you move in the parallel to the x-axis, y-axis, z-axis. Okay, so that's all you're changing. Okay. Okay. What is del u by del z?
X squared times y to the power times 4 times z to the
Yep. So there you go. And what is this vector field giving you? It's giving you how fast u is changing at that location. And it's giving you the direction in which it's changing. Okay, so that if that is the potential energy function of a system, the force acting on that system at any location is negative of the gradient operator. All right, so here's the potential energy function for that system at any location, and here's the force on that system at any location. Okay. Now, if I wanted to get the behavior of the system, if I wanted to calculate the behavior of the system, I would ask you, what is the force on the system at any location? To get the force, you need three functions. But if it was a conservative system, all I need to give you is one function, the potential energy function, 1/3 the information, get the force, and then I can calculate the behavior. All right? So that's what this is about. All right. This slide just shows you that this is indeed valid. So we calculated the potential energy for a spring was 1/2 kx squared, and if you take the derivative of that, you do indeed get the force on the mass that was attached to the spring. Okay. Equilibrium points are defined where the force is 0. Okay. So where is the force 0 for a conservative system? Wherever you have an extrema for the potential energy. So that's equilibrium position, that's an equilibrium position, that's an equilibrium position. And here's an infinite number of equilibrium positions. Okay. This guy is called a stable equilibrium, unstable equilibrium. These guys are all neutral equilibrium points. Stable equilibrium points are, if you disturb the system from that point, the system will bring it back to the equilibrium point. Unstable equilibrium points are, if you disturb the system, it runs away from the unstable equilibrium point. Neutral equilibrium points are, you disturb it from one neutral equilibrium to next one, it'll stay there.
What is the system that was in an unstable equilibrium? Like
So that's a stable equilibrium point. You disturb it from the equilibrium position, it'll come back. That's an unstable equilibrium position. Okay. So for a stable equilibrium position, you see du by dx is an increasing function. For a stable equilibrium position, d square u by dx square is positive. Okay. The curvature is upward.
What was the third equilibrium state, or when it moved, it just
Stayed there, neutral equilibrium position.
neutral?
Yeah. See this thing? This thing is a neutral equilibrium position. So there's the neutral equilibrium position. Okay, why do we talk about this kind of stuff? So here's a potential energy function for a diatomic molecule. Okay. Do you guys know of any diatomic molecules? Hmm? Water is a triatomic molecule. This room is full of diatomic molecules, nitrogen and oxygen. All right. So now the question is, okay, here are two nitrogen atoms. How far apart are they? This room has about 10 to the 28 nitrogen molecules. Okay? And here's the answer to that. Rough answer. Here's the potential energy curve. What this potential energy curve tells you is the following. So here's one nitrogen molecule. Here's another. As you change this distance, the potential energy changes. Okay? So if the nitrogen molecule is too close, the potential energy is that du by dx is negative. This slope is negative. Force is minus du by dx. Okay, this is negative, this is negative, negative, negative is positive. So the force on this guy will be in that direction. If the nitrogen molecule is this far, du by dx is positive. That negative, the force on the nitrogen molecule atom will be in this direction. Okay, so when it's too close, the force is in that direction. When it's too far, the force is in this direction. Where does this guy sit? At the minima of the potential energy. And that is the bond length. Okay. So all you had to do was see this picture and you know the bond length. Okay. And of course there are quantum effects, it'll vibrate and all that. But classically that would be the size of the molecule. Okay. That would be the distance between the atoms. So these potential energy graphs are very useful. Okay, let's say you get on top of a building and throw these balls at the same speed. Which ball will hit the ground with the greatest speed? So initial speed is the same. Except that you're throwing them in different directions. The question is, I'm asking the speed.
It would be the same.
It'll be the same. Very good. So what our friend realized was kinetic energy final plus potential energy final equal to kinetic energy initial plus potential energy initial. The initial launch point is the same. This is the same for all of them. And this is 0 for all of them, so final kinetic energy will be the same. Okay, they'll have the same speed when they hit the ground. What will be different? The paths are different, so the time of flight will be different. This is that path. This will hit the ball, hit the first, second, third, and so on. Okay. All right. This is an interesting problem. Okay. So the problem is the following. You want to get from here to there under the influence of gravity and a normal force. What is the fastest way to get from here to there? Is this the fastest way? This is the fastest way. What is the fastest path? Okay, that was the question. And it turns out the solution, so this is the Brachistochrone problem, and the fastest path happens to be this, and that's a cycloid. And so here's an illustration of that. You see, you release the two balls at the same time. You know, your initial guess would be a straight line path, but this guy, the inverted cycloid, is the fastest path. Yeah. And there's another very interesting thing about this path. I got to show you this graph. It's very cool. Okay, see that? So that's the inverted cycloid. And what are you guys seeing there?
No matter where the ball starts, they all reach the bottom at the same time.
At the same time. Amazing. Okay. So that happens to be the fastest curve, and it also happens to take a specific amount of time. Okay. All right, guys, so that finishes the chapter.